In this lecture, I'm going to be talking about another article about contrastive networks and Siamese network. And this paper, Run Away from Your Teacher, Understanding the BYOL Algorithm by a Novel Self-Supervised Approach. Newly proposed self-supervised framework bootstrap your own latent BYOL that I've explained in a different lecture seriously challenges the necessity of negative samples in contrastive learning. BYOL works like a charm despite the fact that it discards the negative samples completely, and there is no measure to prevent collapse in its training objective. In this paper, we suggest understanding BYOL from the view of our proposed interpretable self-supervised learning. Run away from your teacher, this raft model optimizes two objectives at the same time: aligning two views of the same data to similar representations and running away from the model's mean teacher, the exponential moving average of the history models, instead of BYOL as running towards it. And the second term of raft explicitly prevents the representation collapse and thus makes raft a more conceptually reliable framework. And we provide basic benchmarks of raft and C410 to validate the effectiveness of this method. And they proved that BYOL is equivalent to raft under certain conditions, providing solid reasoning for BYOL's counterintuitive success. So you're familiar with alignment loss from previous lectures and also uniformity loss, that we use these two measures in order to see if a contrastive model is working properly or just it is collapsing to a single point or even a dimensional collapse. It's collapsed to a subspace. So a recently proposed self-supervised representational algorithm, BYOL, hugely challenges the common understanding that the alignment should be balanced by negative samples during the contrastive learning, because it doesn't use negative samples. And it establishes two networks, online and target, approaching to each other during training. The online is trained to predict the target representation, and target is the exponential moving average of the parameters of the online. And the loss of BYOL model at every iteration is this expectation, where two vectors in representation space are automatically L2 normalized. This f theta is the online encoder, and this is parameterized by theta, and q is the predictor network, which is parameterized by w. And x is drawn from the inputs from the data distribution. T1 and 2 are augmented views of a single x. We have two augmented views where T1 from T distribution, and there are two augmentations. The target network is of the same architecture as f theta and is updated by this exponential moving average, and tau is controlling to what degree the target network preserves its history. And the cross-model loss is the expectation of a function f and g over the distribution x. So the BYOL prime loss could be just using the align loss and the cross-model, which is described here, which is a distribution of the augmented data. And this is the architecture of raft and BYOL. The online network is composed of an encoder f theta and an extra predictor q. The mean teacher f psi, f is the exponential moving average of the encoder f theta. So this is the mean teacher, and in the BYOL, the loss is computed by minimizing the distance between the prediction of one view and another view representation, which are generated by DMT. And in raft, we optimize two objectives together. First, we minimize the representation distance between two samples from a positive pair, and then we maximize the representation distance between the online network and its mean teacher. So we have an upper bound for the BYOL loss, and we provide how we derive the upper bound. And for the sake of simplicity, without loss of error, we use T1 to represent a transform input. Then apply Cauchy-Schwarz to that. And here, the positive pair distribution is modeled by this chain rule of the conditional probability. So it's an upper bound. And you see how objective categories there are with respect to the effect constraining the alignment loss. In contrastive methods, the most favorable objective actively optimizes uniformity, including both BYOL prime and RAF with predictor. The secondly favorable objective is the effective regularizer of the alignment, and RAFT remains to restrain alignment loss without predictor, while BYOL fails to do so. And this is a definition of RAFT loss, which is just a linear combination of, so it's a trade-off between cross model and the alignment model. So the consistency when compared to BYOL, our newly proposed method has an effective regularizers for the alignment loss regardless of the presence of predictor. And it has also the interpretability because the mean teacher uses the technique of weight averaging and thus could be considered as an approximate ensemble of the previous versions of the model. Running away from the mean teacher intuitively encourages the diversity of the representation, which is positively correlated to the uniformity. And then finally, we have disentanglement. The learning objective is decoupled into aligning two augmented views and running away from the mean teacher, and hence could be independently studied. And we derive the upper bound of BYOL prime and BYOL and explicitly extract two terms. And in BYOL prime, two terms are simultaneously minimized. But in the raft model, we minimize align, but we maximize the cross model. So the algorithm of raft is first we take the set of images and then the model parameters and predictor parameter. We set the predictor parameters and predictor, then this teacher parameters, and then we for a batch of n images we sample image transformation. We have two transformation, and then we use for the predictor, and then we calculate loss for alignment and cross model. And then we compute the loss gradient, but with respect to theta when we update the trainable parameters as well as the target parameters. And our output is the encoder of theta, which is good representation. But there is a one-to-one correspondence between BYOL prime and raft. The representation space is hypersphere, the predictor is a linear transformation, and only the tangential component of the gradient on the hypersphere is preserved. So we have two objectives that we claim that under the third condition these equations hold. Firstly, we show that the equivalence with respect to theta, and then we differentiate with respect to theta prime. And now suppose Z is a unit vector starting at the origin point, which is perpendicular to the unit hypersphere at the point Z for any vector. And then we can compute the tangential component of the gradient, but because of the initialization, we can show that the gradients are the same.